Okay, we're working in our rate unit and we've learned about potential energy diagrams, and we're talking about the speed of these reactions and what can speed them up and slow them down. Now for each reaction, we can even have different rates. So first of all, it could be different reactions, but we could have the same reactions at different concentrations. We could have different temperatures. We could have catalysts. And in order to calculate the rate of these different reactions, we need to create a formula for each reaction. We do have a general rate formula, and that's the change in concentration over change in time. But if we want the rate of a specific reaction based on the different concentrations that we can have, we need to write what's called a rate law, and our rate law is the formula that we're going to create. So here's our generic reaction. 2A plus B is going to give us C. And basically, we always write down rate equals K, and K is some constant that they will give you, okay? So have to write K, and then we multiply that by the concentrations of our reactants only. There are no products. To each concentration, we raise it to a power. These powers are called orders, and they must be determined experimentally. So I can't look here and figure out what this is. I just have to write a generic X and a generic Y. And we'll work on figuring that out in your next lesson. So let's go over what K is. K is the rate constant, and it's specific to each reaction. It takes into account the temperature, so my K would be at 25 degrees C. If I change the temperature, it would be a different K. It also takes into account the orientation. Does this reaction have proper orientation so it will go very fast, or is the orientation very jumbled and it's very hard for those guys to match up? That would make a slow reaction and my K would be lower. Okay, the other thing it takes into account is the energy of collision. So that has to do with temperature for part of it. Will these reactants hit each other with enough energy to make a reaction and speed up the rate? If we have a lot of energy, our K will be higher. So our K gives us information. If I compare two reactions in two different Ks, if they're similar, if I have a bigger K, I'm going to have a faster rate. It means I probably have a lower activation energy, higher temperature, good orientation, and such. Okay? So let's first work on writing these rate laws. Okay? So we have our generic equation right here, and I am going to tell you that the order of A is 1 and the order of B is 2. Okay, so my rate equals K times the concentration of A, and there's a 1 there, but we usually don't write the 1, right? I'm going to make that go away. And B is to the second order. So now what is the order of the reaction overall? That's adding all these orders together. So 2 plus 1, my overall reaction order is 3. Okay, so remember that our overall order is all the orders of each reactant added. Notice there are no products in our rate law. Rate equals K times the concentration of reactants raised to some power that you will be given or you have to determine experimentally. So if K is very large, we have a much faster rate. If K is large, we have a lower activation energy. Remember, when I lower that activation energy, I speed up the reaction. I have a faster rate. Okay, so if I lower that activation energy with a catalyst or something, I have a smaller hill to get up. It's going to go faster, and that means that I will have a larger K. Notice, if I have a larger K, my rate is faster. Whoop, let's go down. If I have a larger K, my rate is faster. Okay, so here's some examples. Write the generic rate law. Okay, here is my problem. Can you do it? So remember, we don't know what the orders are. They haven't given it to us, so we need to do the generic form, which is rate equals our constant times the concentration of both reactants raised to some power that we don't know yet. Okay, and now I'm going to tell you that the order is F is 2, and the order with respect to C is 1. Now rewrite that rate law. Can you do it? And there we go. F is to the power of 2 because F is the second order, and C is in the first order, so there's a 1 there, and that doesn't do anything, so we don't have to write that 1. So what is the overall order of the reaction? It's 3. Okay, now our last example is going to go into order of 0. What happens if I raise anything to the 0 power? Well, that just anything raised to the 0 power is 1, and 1 times anything is itself, so you can kind of leave it out. So order with respect to P in this equation is 0, and H is 1. So we're going to write the rate law. Rate equals K times H. I left P out because P to the 0 equals 1, and if I just put a 1 there, it doesn't change anything, so you can just leave it out when things are to the 0 order. What is my overall reaction order? Well, I only have one order there, and it's to the first order, so my overall reaction is first order reaction. Okay, so example number 3. I have these two rate laws. They're two different formulas, and I'm going to tell you that they're run at the same concentration and the same temperature. So I am going to tell you that 2 has a much faster rate. So what does that tell us about our K in number 2? Well, it tells us that our K must be bigger, okay, because my rate's faster, okay? Okay, now that you know how to write your equation, we're going to use that equation to solve a problem. So the first thing I just want to be very clear on that people get confused on, when you see square brackets, that means concentration. So instead of writing molarity all the time, we can put things in square brackets. Okay, so if we have it in square brackets, we don't have to write M for molarity, but the square brackets mean concentration in chemistry. So our question is, what's the rate of the following reaction? And they give us this reaction, they give us our K, and they give us our concentration, and then they tell us what order that my reactants are in. So the first thing that you do is you write your rate law. My rate law equals K, A to the first order, B to the first order. So my rate equals K, concentration of A times the concentration of B. Why? Because our concentrations directly affect our rate. The more concentration, the more particles we have, the more collisions we would have, and more of them would be at the correct energy to make a reaction, so our rate would go up. More concentrated, bigger rate. Okay, so when I plug everything in, rate equals my K, which is 2.0, M to the minus 1, S to the minus 1, times our concentration of A, which is 0.5 molar, that's what the brackets mean, times our concentration of B, which is 1.0 molar, and I get a rate of 1.0 molarity per second, and that's what our rate is in. It's a change in molarity per unit time. So let's talk about these -1 units, okay? Note on units. So A to the minus 1 is 1 over A. You guys should know that from your math. So when they put seconds to the minus 1, it means 1 over seconds. When they put seconds minus 1, molarity minus 1, it means 1 over seconds on the bottom, molarity on the bottom. So here I kind of wrote that out. We have 2.0 1 divided by ms. That's what that negative means. And then I multiplied it by molarity, which crosses that out, and I multiplied it by molarity again, which leaves a molarity on top, okay, and my seconds on the bottom, which is why I have molarity per second.